Hey everyone, and welcome to this explainer. Today, we're diving into something that honestly blows my mind. We are going on a journey into the sheer engineering marvel of aviation safety. For a lot of us, flying feels like this unnatural defiance of gravity, right? We walk onto this heavy metal tube, hurtle through the sky at hundreds of miles an hour, and just kind of trust that we're going to arrive safely. But behind the scenes, there is this hidden, incredibly intricate world of uncompromising engineering. And it's all designed specifically to keep these machines perfectly in flight, no matter what Mother Nature or mechanical stress throws their way.
100,000. Think about that number for a second. That is the staggering number of commercial flights taking off around the world every single day. We're talking millions of people, suspended miles in the air, safely crossing vast oceans and whole continents on a daily basis. Honestly, given the sheer volume of metal occupying the sky at any given second, pure statistical logic might tell you that things should be going wrong constantly.
Which leads us straight to a question that really taps into our deepest fears about flying. Why don't airplanes constantly crash? Today, we're going to explore exactly how every single inch of a modern aircraft is rigorously engineered to answer the ultimate what if with a totally reliable, proven failsafe. We're going to look at how human ingenuity neutralizes danger, keeping the airplane safely in flight from takeoff all the way to touchdown.
Okay, let's get right into it with Section 1, Battling the Elements, Surviving Extreme Forces in the Sky.
So, if you've ever been in a window seat during some rough turbulence, you've probably seen the wings flapping up and down out there. And yeah, it looks absolutely terrifying in the moment. But actually, scratch that. It's exactly what keeps you safe. It beautifully illustrates a core principle of aviation engineering. Flexibility is strength. Airplane wings are explicitly designed to bend, not break. During manufacturing, they go through this intense stress testing, where machines pull the wings upward until they nearly touch at the top. This ensures that their flexibility absorbs all those violent, chaotic forces of turbulent air. If the wings were totally rigid, the stress would literally cause the metal to snap. Instead, they act like giant, flexible shock absorbers, keeping the plane completely stable and safely in flight.
And this environmental protection covers the weather, too. Commercial planes actually get struck by lightning way more often than you might think, usually about once a year per plane. So why doesn't a massive bolt of electricity just drop a plane out of the sky? Well, it all comes down to the Faraday cage effect. Basically, this is an enclosure that blocks electromagnetic fields, safely distributing electrical currents around its exterior. The aluminum fuselage of the plane acts as a highly conductive shell. When lightning hits, that immense electrical current is safely and instantly distributed around the exterior skin. It just travels along the outside and exits right out the tail of the wings. The passengers, the fuel lines, the computers, completely untouched.
Moving right along to Section 2, Secrets of the Cabin, Engineering Life Support at 35,000 feet. We're heading inside the aircraft now to see how the cabin actively protects us from the deadly, freezing atmosphere just inches away.
Have you ever wondered why airplane windows are always round and never square? The aviation industry actually had to learn this vital lesson the hard way. Back in the 1950s, the de Havilland Comet was celebrated as the very first commercial jetliner. It flew higher and faster than anything before it. But it suffered a series of tragic disasters where the aircraft broke apart mid-flight. When investigators painstakingly put the wreckage back together, they found the culprit: square windows. The sharp 90-degree corners of a square window concentrate structural stress from the repetitive pressurization of the cabin, which eventually causes the metal to fatigue and tear. Modern round windows fix this by allowing that intense pressure to flow smoothly around the glass, giving a perfectly even stress distribution and keeping the whole cabin completely intact.
Now, here's another common anxiety I hear all the time. What if a panicked passenger just tries to pull open the cabin door mid-flight? Hollywood movies love this dramatic trope, but physics says absolutely no way. It's impossible. Commercial airplanes use what's called a plug-type door. As the plane climbs into that thin atmosphere, the cabin is pumped full of air pressure so we can breathe normally. This creates a massive pressure differential between the inside and the outside sky. That pressure effectively wedges the door firmly into its frame. It's sealed shut by immense cabin pressure, acting like a giant immovable stopper. Because the door has to open slightly inward before it can swing outward, you would literally need superhuman strength, thousands of pounds of pulling force, to open that door against the internal pressure.
But what happens if, by some rare chance, that pressure is lost? We all know the safety briefing. The oxygen masks drop. However, you might have heard this slightly terrifying fact that these masks only hold about a 15-minute supply of oxygen. Sounds alarming, right? But the crucial point here is that it makes perfect sense when you look at the sequence of events. Step 1, the masks drop to give you immediate life-saving air. Step 2, the highly trained pilot immediately initiates an emergency descent. Step 3, within just a few short minutes, the plane reaches a safe altitude of under 10,000 feet, where the outside air is thick enough for everyone to breathe normally. So, that 15-minute supply isn't some dangerous cost-cutting measure. It is perfectly calculated and provides way more time than the pilots actually need to get you down to breathable air.
All right, Section 3, Extreme Emergency Engineering, Redundancy in Motion. This is where we shift from surviving the environment to surviving mechanical failures.
Let's talk about the engines. What on earth happens if one completely fails while you're cruising over the middle of the Pacific? Enter a super strict certification called ETOPS, or Extended Range Twin Engine Operational Performance Standards. It's a mouthful, but basically, it certifies planes to safely fly long routes with only one working engine. This guarantees that a modern plane can maintain its crucial systems, navigate, and land safely even if an engine gives out. Combine that with extreme pilot training and advanced simulators for this exact scenario, and it means losing an engine is for sure a headache, but it absolutely will not stop that plane from staying in flight and getting you to a runway.
And when it is finally time to hit that runway, we rely heavily on the landing gear tires. Just think about the physics here. An airplane tire goes from a complete standstill to spinning at 170 miles per hour in a fraction of a second, all while slamming down onto the tarmac carrying hundreds of tons of weight. Why don't they just pop like balloons? Because they are engineered to extreme survival parameters. First, they have extreme inflation pressure, often 6 times that of a standard car tire, and they're filled with non-combustible nitrogen gas to prevent fires. Second, they're densely reinforced with advanced synthetic materials to give them a massive weight load capacity. And finally, their treads have incredible high-speed friction endurance. Under standard landing conditions, these things are practically indestructible.
Which brings us to our final section, Section 4. Learning from every flight, the ultimate fail-safe. Now, what's really interesting about this slide is the famous black box. We all know the term, right? Those nearly indestructible flight data and cockpit voice recorders that tell investigators exactly what happened after an impact. Well, ironically, they aren't black at all. The black box is actually bright orange. This is a highly intentional, very practical design choice. Along with their built-in underwater locator beacons, that unmistakable, high-visibility orange color is specifically meant to heavily contrast with natural environments, like the bottom of the ocean or a dense forest. It dramatically aids accident investigators in finding them as quickly as humanly possible.
And finding those boxes quickly is absolutely critical for the entire industry. Modern aviation is built on 3 key pillars: relentless accident investigations, decades of lessons learned, and continuous engineering upgrades. Every single tragedy over the past century has been meticulously studied to engineer a safer future. When a vulnerability is found, the rules are instantly rewritten, and every single plane is physically updated to meet that new standard. It's this continuous loop of learning and upgrading that has transformed commercial aviation into one of the safest forms of transportation in human history.
So I want to leave you with this final thought. Next time you walk down that jet bridge and board a plane, will you see a fragile metal tube, or will you see the safest machine ever built? Keeping a commercial aircraft safely in flight isn't magic. It is the breathtaking culmination of decades of brilliant human problem-solving. From wings that bend to absorb the wind, to windows perfectly shaped to distribute stress, to an industry that is totally obsessed with redundancy, every single detail is purposefully designed to keep you safe and keep that aircraft soaring. Thank you so much for exploring these incredible engineering secrets with me today on this Explainer. Keep wondering, keep learning, and safe travels.